Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I bring you the Organic Chemistry one-slide guide to hybridization and geometry. The question, of course, is how do I determine an atom's hybridization and electron geometry? This is something that students learn in general chemistry, and it's pretty simple. We count the number of sigma bonds, including any undrawn carbon-hydrogen sigma bonds, and the number of non-conjugated, we'll go over that in a second, lone pairs on it. If we have 4 total sigma bonds and non-conjugated lone pairs, the atom is sp3 hybridized and has tetrahedral electron geometry. If 3, it's sp2 and trigonal planar, and if 2, it's sp and linear. Now in organic chemistry, we learn about conjugated versus non-conjugated lone pairs, and this is something that's not discussed in general chemistry. And this is important because it affects both the geometry and the hybridization. So how do we tell if a lone pair is non-conjugated? Well, first we're going to determine if the atom that has the lone pairs has any pi bonds. If yes, the lone pairs are non-conjugated and they do contribute to the atom's hybridization. If no, we have to take another step. We determine if the atom that has the lone pairs is adjacent to another atom that is sp2 or sp hybridized. In other words, if the lone pairs are adjacent to another atom with a p orbital, then one of the lone pairs is conjugated and does not contribute to the atom's hybridization. If no, meaning there's not an adjacent atom with a p orbital, then all the lone pairs are non-conjugated and they do contribute to the atom's hybridization. A question that often comes up is, how do I deal with radicals and carbocations? Well, radicals on bonded atoms always are found in p orbitals, and they have a minimal effect on the geometry. So, all you need to do is count the number of sigma bonds, as usual, on the atom. For carbocations, a carbocation implies the atom has an empty p orbital. Once again, we're simply going to count the number of sigma bonds, as usual. What about if there's a positive charge on a non-carbon atom? Well, for this, we simply ignore it. And once again, we're going to count the number of sigma bonds, as usual. Last up, what about an atom's molecular geometry? Well, in organic chemistry, we typically just focus on whether an atom is tetrahedral, trigonal planar, or linear, and we don't really care about the molecular geometry such as trigonal, pyramidal, and bent, because they aren't very relevant to reactions. Let's do some rapid fire on a bunch of examples. On the bottom left, we have an arrow drawn to a carbon, and we have 2 visible sigma bonds, but carbons need to have 4 bonds, so there are 2 undrawn carbon-hydrogen sigma bonds as well. So that gives us 4, making this sp3 hybridized. On the next molecule over, we have a negative charge, implying there's a lone pair on that carbon. Now, that lone pair is non-conjugated because there are no adjacent atoms with p orbitals, and the carbon itself does not already have a pi bond on it. So, that counts for the hybridization. So we have 2 sigma bonds that are drawn, 1 carbon-hydrogen bond that is not drawn, and a lone pair. So again, that's 4, meaning this is sp3 hybridized. On the carbocation, again, we can ignore that carbocation and just count the sigma bonds, so that's 3, so that is sp2 hybridized. Next, we have 2 drawn sigma bonds and 1 carbon-hydrogen sigma bond that's not drawn, so that's also sp2 hybridized. On that alkyne, looking at the carbon on the very right that there's an arrow drawn to, we have 1 sigma bond to a carbon, and then we have an undrawn carbon-hydrogen sigma bond as well, so that's 2, making this sp hybridized. For the nitrogen on the next molecule, there is a lone pair on it. Remember that nitrogen should have 8 valence electrons around it, so there's 3 sigma bonds there, which means we need to have a lone pair. So there is an undrawn lone pair on it. Now we have to say, is that lone pair conjugated or non-conjugated? Well, I don't see any pi bonds on the nitrogen, so we have to go to our next step, and we look at the atoms adjacent to it. And it looks like the carbon to the left and the carbon to the right are both sp2 hybridized. In other words, they have a p orbital, which means that that lone pair on the nitrogen is conjugated and does not contribute to the atom's hybridization. So in other words, we just count the 3 sigma bonds on it, so it's sp2 hybridized. On the next molecule over, once again, we're looking at a nitrogen, and it has 3 bonds on it for 6 valence electrons, so there must also be a lone pair on that nitrogen as well. In this case, the lone pair is non-conjugated because the nitrogen already has a pi bond on it. So since the lone pair is non-conjugated, it does contribute to the atom's hybridization. So I count 2 sigma bonds and 1 lone pair for 3, making this sp2 hybridized. On the next molecule, looking at the oxygen, it looks like oxygen is going to need 8 valence electrons as well, and I see 6 on it. We have the 2 bonds to the carbon, and then we have the oxygen-hydrogen bond. So the oxygen has a formal charge of +1, but we can ignore that, because what really matters is that there's a lone pair on that oxygen. So the lone pair is non-conjugated because the oxygen already has a pi bond on it, so it does count towards the hybridization. So that's 2 sigma bonds and 1 lone pair, making that sp2 hybridized. The next carbon ion is different than our second molecule that we said was sp3 hybridized. That's because the lone pair on this one is adjacent to an atom that is sp2 hybridized, in other words, an atom with a p orbital. And because it's adjacent to an atom with a p orbital, that lone pair is conjugated and therefore does not contribute to the atom's hybridization. So that means we have 1 sigma bond that's drawn, 2 sigma bonds to hydrogens that are not drawn, and the lone pair does not count. So that's 3, meaning it's sp2. For the oxygen on the next molecule, there are 3 sigma bonds. That's 6 valence electrons, so there must be a lone pair on it as well. Even though there's a positive formal charge on the oxygen, we can ignore it again because it doesn't matter. So we have 1 lone pair and 3 sigma bonds, so this is sp3 hybridized. And the last molecule, looking at that oxygen has a sigma bond to a carbon and to a hydrogen, and there are 2 lone pairs on it. We'd normally think that that's sp3 hybridized. However, the oxygen is adjacent to a carbocation, and that carbocation, carbon, definitely is sp2 hybridized because it has a p orbital. So that means that one of the lone pairs on the oxygen, since it's adjacent to a p orbital, must be in the p orbital itself. It's conjugated, and therefore it does not contribute to the hybridization. So in other words, we have 1 lone pair that does contribute, 1 sigma bond to a carbon, 1 sigma bond to a hydrogen. So that gives us 3 total, so it's sp2 hybridized. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.